Hi guys, so let's do section 10.2 part 1. We did last class, actually the two previous lessons, not classes, we didn't have class. The two previous lessons we did confidence interval and hypothesis test for a difference in two proportions. So of course we want to do the same thing for comparing or a difference into means. Okay, and so again, this is really a very much of a parallel lesson to lesson 10.1. So I don't want to go over this too much. I'm not going to belabor this too much. I'll let you read over this, but basically you have the same thing going on if the sampling distribution of my first sample mean is approximately normal and sampling distribution of my second sample mean is approximately normal, then the approximate sampling distribution of the difference of those two sample means will be approximately normal. And we know this from chapter 6 and 7. Okay, and then we also know that the mean of the difference in sample mean sampling distribution will be about the difference of the means as illustrated here, and the standard deviation will be that. Okay, which remember when we subtract random variables to find the standard deviation, you actually add their variances. So we had a long conversation about this thing in chapter 6. And so, in any case, this is what we get. We've done this before. I don't want to really belabor this too much. So theirs would be my resulting mean for a difference in means sampling distribution, and this would be my resulting standard deviation for a difference in means sampling distribution. Okay, so there's a summary of all that information, and I'll let you read this. It says shape if each... Oh, and remember, this is not the large counts condition. For means, we are talking about the central limit theorem. So it says the sampling distribution of the difference will be approximately normal if each individual sampling distribution is approximately normal, which means that the CLT is met. Now you remember what to do if the CLT doesn't apply, then you have to look at the graphs and make a decision about normality of the population based on the graphs. Okay? And then the center, we just said, is that, and the standard deviation is about that. As long as you're not sampling more than 10% of the population. All right? So, here's a little example that just asks you to put this into practice. So they say, I'll read the whole long thing with you and then do it very quickly, but this is a little bit below your abilities and skill set. In any case, it says, based on information from the U.S. National Health and Nutrition Examination Survey, NAHANES, the heights of 10-year-old girls follow a normal distribution with this mean and this standard deviation. The heights of 10-year-old boys also follow a normal distribution with this mean and this standard deviation. Okay, a researcher takes a random sample of 12 10-year-old girls and a separate random sample of 8 10-year-old boys in the United States. After analyzing the data, the researcher reports that the mean of the boys is larger than the mean of the girls. Alright. The mean of the boys is larger than the mean of the girls. Okay. Describe the shape, center, and spread of the sampling distribution of the difference in sample means. Girls minus boys. Alright? And so, this is interesting. We have very, very small sample size, 12 and 8, but we're told that the population distributions are normal. So the first two sets of numbers we were given, and it says normal distribution here and normal distribution here. So since the population distributions are normal, so we say since the population distributions are normal. The sampling distribution of x bar sub f minus x bar sub m is also normally distributed. Okay, so since the population distributions of each population is normal, then when I sample from each of those, the sampling distributions are automatically normal, and if the sampling distributions are normal of each individual sample, then the difference is then automatically also normal. That's a bit of a technical point from chapter 7, I think. Okay, and then center. So center for us should be easy to calculate. The mu sub x bar sub f minus x bar sub m. So the mean of the difference in sample means would be equals to the difference of the means of the individual sampling distributions. Okay, and so this would be equals to this minus this. Okay, so because this is equal to that and this is equal to that, because the mean of the sampling distribution of the females distribution would be exactly equal to the population mean for females, and so on and so on. So we have those two numbers. We have 56.4 and 55.7. So we can say 56.4 minus 55.7, and that would give me 0.7 inches. Okay, and then we have to use our formula here for standard deviation, and standard deviation of the difference in sample means distribution would be this, which is the variance of the female distribution over the sample size of the female distribution. I guess we could write it like that, plus the variance of the male distribution over the sample size of the male distribution, something like that. Okay, and then we just fill those numbers in. And so the standard deviation of the girls or the females was 2.7 squared over the sample size, very small, of 12, and then plus this one would be 3.8 squared over that small sample size of 8. And if you punch that whole unfortunate mess in your calculator, you get this. Okay, so we have described the sampling distribution of the difference in sample means female minus male. Okay, so we have the shape, center, and spread. All right. Okay, so then, now that we understand the sampling distribution, now we want to be able to use this to build confidence intervals. Of course, why not? We want to do inference. We want to do confidence intervals and hypothesis tests, so we can derive some meaning from subtracting two means. Meaning from subtracting means. And so, in any case, so here's the conditions, and this should not look very surprising to you. Very similar idea. The data come from two independent random samples or from two groups in a randomized experiment. So there was random sampling from two populations, or we did random assignment to two different groups. One is usually treatment, one is control. Okay? And then 10% condition when sampling without replacement. check the 10% condition. Make sure you're sampling less than 10% of each respective population. All right. So again, two levels there. You want independence between the samples themselves or the treatment groups themselves. That's okay because of random assignment or random sampling. And then you want independence within a group. For experimentation, that's usually safe to assume that people's responses to treatment are independent of each other, or something like that. And then if you're sampling, you want to make sure that you're sampling less than 10% within each population. Okay, so that's actually a lot of thinking there. And then so random, independence, and then normal. Okay, the normal condition. The normal condition is the same as it was for a confidence interval or a hypothesis test for a single mean. You have to try and meet the CLT with a large sample size. And if that doesn't work, okay, so if either population distribution has unknown shape and the corresponding size is less than 30, use a graph of the sample data to assess normality of the population distribution. So, do not use two sample T procedures if the graph shows strong skewness or outliers. So if there's outliers at all, even if the CLT is met, don't do it. Okay, and I know that one of our homework questions, they actually did say it's okay, but the rule that we're given is that we shouldn't do that. All right. So what this means for you, if the sample size is not at least 30, then you have to make two box plots and look at the box plots and say, oh, these box plots look okay based on the sample size, and therefore I can continue and assume there's no reason to doubt normality in the population. Okay? Those are the conditions. And then if the conditions are met, so here we are when the conditions are met, a C%, most of the time 95% confidence interval for mu1 minus mu2. The difference in means in the population is this. Okay, standard T procedure, I'm just subtracting the two means and I'm adding their variances and taking the square root to find the standard deviation of the difference. And there's my T star value. You can find that using inverse T again. And that's all you need to know. All right, and of course, you must always report degrees of freedom. So degrees of freedom must be reported. And degrees of freedom is the smaller of n minus 1, n1 minus 1 or n2 minus 1. The smaller of them. But actually, you might use this sometimes, but we are going to use our calculator to build confidence intervals. And that's going to give us the degrees of freedom. And you're going to get some strange degrees of freedom. It's usually some decimal degrees of freedom or something. There's a very complicated formula for this to calculate it the way that the calculator does. You don't really have to worry about that. The calculator does it for you, and you just report what degrees of freedom the calculator used. Okay? So, that's that. So, there's the gist of it. Let's go and actually get in there and do one. So, it says example 2, the weight. Now, this is real. I went and looked this up, all right? This is not some made-up fairy tale. This is a real place. The Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in relatively undisturbed state for hundreds of years. So there's a lot of words here. I'm not sure how much of this you understand, but old-growth forest means something specific. It's forest that has been there for probably thousands of years, that has not been chopped down and replanted and burned down or whatever. It's really an old forest, all right? And so this is what they're saying. So they're describing to the Wade Tract Preserve, and it says, one question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the north and the south of the forest compare? To find out, they took random samples of 30 trees from each half and measured the diameter at breast height. Again, if you think about the logistics of this, someone doing research, what does diameter at breast height mean? How do you define that? Whose breast height are we talking about? This stuff is pretty complicated and technical, but so they have some way of measuring the diameter of the tree at a specific height, what they're calling breast height. Okay, and comparative box plots of the data and summary statistics from Minitab are shown below. Well, you should be happy about this. Sample size is 30, and the box plots don't show any outliers, so that should make you happy for the normal condition. Okay, this is the thought that should cross your mind first, but okay. We're not there yet. They say, based on the graph and numerical summaries, write a few sentences comparing the sizes of longleaf pine trees in the northern half and southern half of the forest. All right, so this is review from chapter 1, actually. We learned to make box plots in chapter 1. We learned to compare distributions in chapter 1. And so this is, I think this is a SOX question, okay? Way back when SOX. All right, so SOX was shape, outlier, center, spread. Okay, so let's talk about the shape. So we say the distribution of what DBH measurements. Okay, DBH measurements. Okay, measurements. In other words, diameter at breast height measurements. Okay, the distribution of those measurements in the south. And what would we say this is in the south? That looks like it's fairly strongly left skewed. Okay, is strongly left skewed, while the distribution of DBH measurements in the north is moderately right skewed. Maybe not as badly as the south, but I would say maybe moderately or also strongly. I think you can use either there. Let's go strongly. Okay, is strongly right skewed. Okay, so this is a comparison. Remember, comparison means you have to say one is bigger than the other, greater, less than, more, less than, stuff like that. Okay, shape, we can't really do that. You just describe the shape. Outliers, you just say neither distributions or neither distribution has any outliers. Okay, and then what else are we saying? Outliers, center, spread. Okay, so they gave us the mean and they gave us the standard deviation. All right, so now I have to make a direct comparison using words like larger, smaller, stuff like that. So we say the DBH measurements in the north. Okay, in the north are have a lower mean, and look at the median. Where's the north? The median is also smaller. Okay, in the north have a smaller median, then the dBH measurements in the south. Okay, and you can include the numbers. You probably should include the numbers. Let's say in the north, smaller median than the south, and let's say, and also a smaller mean at, let's do, what would the median be about? Maybe about, I don't know, 16 or something. So at mean of 23.7 and maybe about 16. For the north, and mean maybe about 34.53, and median here about maybe 37 for the south. Okay. All right, so we've said that the center for the south is greater than the north. Okay, and we reported both measures, mean and median. And then standard deviation for the north is larger than the south. Okay, so we say that the standard deviation and IQR, okay, and IQR for the north is greater than the standard deviation and IQR in the south. Okay, IQR in the south. Wow. All right. That's remember, you have to use words like smaller or greater when you're talking about spread. When you talk about spread and center. Okay, and then we described the shape, and there were no outliers. All right, this is a classic chapter 1 type question. All right, so then here's what we really got to this section 4 was to do some inference, which is construct a 90% confidence interval for the difference in the mean dBH of longleaf pines in the northern and southern halves of the Waite-Tract Preserve. All right, so state. Let's follow our 4-step process. State, we want to construct a 90% confidence interval for mu1 minus, well, actually maybe we should call this mu, which way would I want to subtract? Maybe we want to subtract the north from the south, since the north is smaller than the south. Okay, so we want to do mu sub s minus mu sub n, something like this. Okay, where now we have to define stuff again, where mu sub s is the true or population mean diameter at breast height dBH of all trees in the south of the forest, or southern half, I guess is more precise, of the forest. And please, let's get this out of the way right now. And mu sub n, don't do this business. Ditto, ditto, ditto. Please don't do that. That's not good at all. That'll get you marked down by me on the AP exam, and it's just poor communication. No one does stuff like that, okay? Mu sub n is the true mean dBH of all trees in the northern half of the forest. Okay. Whew, that's a lot of definition before we can even start. All right, then plan, and we have to name our procedure if conditions are met. We will construct a 2-sample t-interval for mu sub s minus mu sub n. Okay, here's the name of our procedure, 2-sample t-interval for that. Alright, let's do conditions. Random. Okay, so what do we have? Researchers took random samples of 30 trees from each half. Okay, so we just say researchers took random samples from each half of the forest. Okay, took random samples from each half of the forest. Okay, fine. Normal. Good news here. Normal. Yay. We can say since both samples are n equals 30, okay, we may assume normality of each sampling distribution by the CLT, okay? And I should say approximate normality, okay? Of each sampling distribution by the CLT, just say the normal condition is met, okay? So since each sample's sampling distribution is approximately normal, then the difference sampling distribution is also approximately normal, okay? And then independent or independence. So we have to establish that the samples are independent. So we just say since both samples of trees are random samples from different halves of the forest, okay, halves of the forest, it is safe to assume that the samples are independent of each other. Remember, I'll draw a little picture here again. We want to do this stuff. Here's my northern half sample. Here's my southern half sample. We're establishing this right now, that they're independent of each other. And then we have to check 10% condition to establish this, which says that they're within the sample, they're independent of each other. Okay, within their population, within the sample that I took from the population, they're independent of each other. So now I have to check 10% condition. We don't know how many trees there are. If it's a big forest, we just have to say we have to assume that there are more than 300 trees in each half of the forest. Okay, which seems reasonable for a big forest, then we can say the 10% condition is met. Okay, so we checked independence, yay, we're happy. So now we have the do step, and that is to do the math. So let's do the math. It's x bar sub, which way are we subtracting? S minus x bar sub n plus minus t star times the standard deviation, which is s sub s squared over n sub s plus s sub n squared over n sub n. That's horrible. In any case, so we get this, and let's plug in the numbers. You can refer back again here. Everything was given to you nicely, so you don't have to worry too much. So you get what? 34.53 minus 23.70. Make sure you write that in parentheses, otherwise you're doing something different. Remember, now here's the trick. You have to find T star. Okay? You have to go find T star. This is tricky. I wouldn't write anything. I would go, and I think it shows up here. Does it? No, it doesn't. Doesn't show up here. Okay. Yeah, I think if you do T star, you have to go and find this. This is weird. Let me just put it out there. This is weird. So I'm going to leave that blank, and I'll show you how I do this, okay? I'm going to fill this in, and this is 14.26 squared over 30 plus 17.5 squared over 30. Problem is, I can go find T star by doing inverse T with the specific degrees of freedom. The textbook said earlier, use the smaller degrees of freedom n minus 1 or n1 minus 1, n2 minus 1. In our case, that would be 29. Okay, if you do that, I think you get 1.699. But actually, when we go do the test on our calculator, we're going to get a different degrees of freedom. So this is very, very tricky. You have to work this backwards. So what I would do at this point is don't write anything else. Go to your calculator, all right, and get your do the test on your calculator. So you go to the calculator, and the test is called you go stat test, right? Stat test, and you go to 2 sample t interval. Okay, 2 sample t interval. So there was t interval for a single sample. Now we've got 2 sample t interval, and then you enter in the stats because they gave us stats and they didn't give us data, and you enter all that stuff in. Okay, and when it says pooled, just say no. All right. We'll talk about pooling later, but just say no for now. Now, this is confusing because we had a pooled proportion or a combined proportion for a hypothesis test for a difference in proportions. That's different here. Okay, we're doing means here, so this is a different thing. So this is no. This is no. We'll talk about this later. Why we say no here. Okay, so just say no, and then use your confidence level 90%, and then you get this. So you get your interval, and you get your degrees of freedom. Now look at the degrees of freedom. It's not actually, let me highlight that, zoom in on that. The degrees of freedom that the calculator uses is not 29, which is what the textbook said we can use. So what I do if I were you is take this number and do an inverse t. Do an inverse t with this degrees of freedom. And that gives you the t star value. If you use this degrees of freedom, you get a t star value of 1.673. Okay, so that's what I would do if I were you. So then I would come back here and say, let me just do a different color too. 1.673. That's my t star value. Because I use the degrees of freedom of 55.728, which comes from the calculator test. So you must be accurate in what you're reporting. Okay, so this is the one drawback of using the calculator and not punching everything into your calculator. But I still think it's better than trying to come up with a confidence interval by directly punching all these numbers into your calculator. If you want to do that, then just do T star with 29 degrees of freedom, and then just change this T star to that one. All right, and so what you get is this. The confidence interval was given to us down here. There it is. So it's about 3.936 to 17.72. All right. So there's the confidence interval. Thank goodness we got through that. And then you say conclude, and you conclude. So how do we conclude? You interpret your confidence interval. So we are 90% confident that the interval from 3.936 to 17.72 centimeters. This was the unit, okay? Centimeters contains the true mean difference in dBH between, and you have to have the order correct here, trees in the south and trees in the north, or northern half of the forest, or however you want to write that. Okay, and what was the question? Just construct and interpret. Okay, technically what we can say now is we're 90% confident that trees in the south are taller than trees in the north. Okay, according to our interval. Any case, I mean not taller, sorry. They have a bigger diameter. Okay, they have a bigger diameter. All right, guys, I hope that helped you. Let me know if you have any questions, okay?